Buenas tardes, gracias por venir al Museo de la Ciencia y del Cosmos de Tenerife. Hoy contamos con la segunda charla pública de la Escuela de Invierno del Instituto de Astrofísica de Canarias, la cual finaliza hoy después de 2 semanas. El pasado viernes tuvo lugar la primera de estas charlas públicas y por si se lo han perdido o quieren escucharla de nuevo, la pueden encontrar en YouTube en el canal Museos de Tenerife. Recordarles que esta charla será en inglés. El conferenciante que tenemos hoy es el profesor Malcolm Longer, de la Universidad de Cambridge, también profesor regio de astronomía de la Universidad de Edimburgo. Ha sido director del Observador Real de la misma ciudad y director del laboratorio de Cavendish durante 8 años. Tiene numerosos trabajos de investigación, autor de 8 libros de astrofísica y cosmología, causando así un gran impacto en la comunidad científica de estos campos. No les entretengo más y doy paso a Malcolm Longer. Muchas gracias.
Thank you. Good evening, and first, my apologies for not speaking in Spanish. It is non-existent, but I will speak clearly and distinctly in Scottish so that you can understand everything. I've entitled this talk, The Astrophysics and Cosmology of the Future, particularly wanting to encourage young people, you have got to take the disciplines from where we are now into the future. Fortunately, my definition of young means younger than me, so that includes everyone. So it is a challenge for everyone. Where are we today? If you say, what does the astronomical landscape look like for instruments? This is what it looks like. These are just samples of where we are with fantastic instruments that I certainly could not have dreamed of when I was beginning to do research. We've got in the radio wave band the very large array in the United States. We've got the ALMA millimeter wave array in South America. We've got the Planck, which has completed its mission, but has impacted everything in cosmology. We've got the ESO VLT. We've got the JWST, the James Webb Space Telescope, which, to my amazement, is working perfectly. It's absolutely amazing. And then we've got new instruments like LIGO, as well as other I put here, like neutrino astronomy and so on. It's a fantastic epoch that we're living in, including, of course, the gravitational wave experiment there. So what are the challenges today? Now, I'm going to emphasize that this is a multiply connected discipline. In other words, you cannot really work with one area without watching what is happening in the other areas. And that makes it very exciting, because there is new astrophysics at the interfaces between all of these. So in the next little while, we're going to uncover where we are in exoplanets, star formation, physics of stars, black holes, gravitational waves, cosmology, evolution of galaxies in 50 minutes. Okay? But remember, the thing to look out for is how one area impacts another, because that's where lots of the most exciting things always happen. Well, I'm going to start with exoplanets. And again, this was discovered in 1995. And here's a picture of Didier Queloz and his... do I have a pointer? No, I don't have it. It's if it was... This is showing the people who discovered the first really utterly and totally convincing example of an exoplanet, Didier Queloz and Michel Mayor. Didier was a graduate student when he discovered that, which resulted in his Nobel Prize. That's an encouragement for all the young people in the audience. That's very kind. Thank you very much. That's good. So this is Didier and this is Michel Mayor. And here's the instrument that he used. It was an extremely highly stable spectrograph on a 2-meter telescope at the French Observatoire de Haute-Provence. And that is a beautiful piece of instrument, not a big one, but one which was extremely stable. And that's what you needed. I love the technology of cosmology, the technology of how we do these things, because it's pushing us beyond what we would expect we can do. Well, the way they discovered it was by the standard way of measuring the motion of the primary star caused by the orbit of the planet about it. And it results in Doppler shifts, which means that you can look for this signature in the observations. And this is what they discovered. Absolutely fabulous, totally and utterly unconvincing. There's evidence for the planet going about the stars. But it's only got a 4.2-day orbit with a small ellipticity, and so it must be very close to the star, not like our own sun, which is at a respectable distance, which I will show you just in a moment. So the other way of doing it is to look for the occultations. And so here's a little planet going in front of the star, and there's a little dip when it goes in front of the intensity, but only at the 1% level. So that needs fantastic photometry, very, very stable instruments again, and that was discovered a year later. Here again is the discovery record of this occultation caused by a star going in, a planet going in front of the star. But these are very, very tiny changes. That technique was brilliantly exploited by the Kepler satellite, which actually just stared at one point in the sky for a long time. Here's the Kepler mission here, and there is the huge array of CCD detectors, and they just stood there and looked. Now that, I think, is non-critical. That is non-critical. You will have to survive a little bit more. That's right. So these are these huge CCD detectors, and they just stared at that point on the sky, and then they could watch for these little occultations happening. And that produced a really, really beautiful picture like this. So there are all the CCD detectors. Earth-sized objects are blue. And then the larger ones, here giant planet size, Neptune size, they're the different colors. So it's really fantastic what you see there. Now, this then is the rate of discovery of exoplanets. Just this week, there are more than 5,000. And this picture, you will notice, was taken on the 27th of November. That's just this week. So this is right up to date. I will give you right up to date data you set on everything. Now, this is the great spike, is Kepler. That's when Kepler discovered all of these ones here. But you see underneath, we've got this steady increase, and this again is just where we are standing this week in the detection of the exoplanets. Well, just one or two nice things I like about this. Here's the orbital periods. And this is going from here 1 day, up 10 days, 100 days, 1,000 days, and you'll see that 10 days is it's a good orbital period to detect. It's difficult to do the very long ones, and again, 1 day is very, very short. So these are the periods. The other thing is the huge range of ellipticities of these orbits, which is it's not like our solar system. Here, if you're at this end of the diagram, they're almost circular. At this end, they're very, very elliptical. And that's very bad, because that means when you're at the periastron, you are going to be very close to the star, and you wouldn't want to be there. So don't look there for life. That's for sure. But if we put on here where our planets are, there's Venus, Earth, Jupiter, quite nicely, reasonably circular, but still enough to give us seasons and things like that. And here's just another one. What about the masses of the ones that have been discovered? Here they are from the mass of Jupiter, 1/10, 100th, 1,000th of the mass of Jupiter, and there are the planets in the solar system, where they sit on this diagram. So you'll see that the Earth, we're down at this part of the diagram, where it's quite difficult to pick them up. You know, they're just technologically, the technology limits you to how low masses you can actually see it. Well, of course, the thing that we want to do is to look and see what the properties of the atmospheres of these planets are. And we do it by this very nice technique of, first of all, taking a spectrum with both the planet and the star. And then, when the planet goes behind the star, we take the spectrum of the star and then subtract them. And that's all you do. But golly, it's technically very complex to be able to do that. But then you can then try to look for the lines which appear in there. And already many important molecules have been discovered: water vapor, sodium, carbon monoxide, and carbon dioxide. And this is what one hopes to be able to do. You can identify bits in the optical infrared spectrum which have got, for example, carbon dioxide possibly suggests volcanic activity. Methane indicates anaerobic bacteria, and so forth. You can identify features which give us clues about what's going on in the atmosphere. Well, here is the James Webb Space Telescope results of an exoplanet atmosphere just from a couple of months ago. And these are, again, the various instruments. And you can see you're getting peaks in the observations. Here's carbon dioxide. Look at that. Absolutely fantastic. It actually works. You know, this way of actually looking for the chemical composition of the planetary atmospheres. So this is just with the earliest release observations by the JWST. So now we'll probably get about 10 years out of the JWST, and you can do keep watching for all these wonderful things that will come about. But the millimeter wave band is very crowded. And you know, if you're not a chemist, you may say, oh my God, you know, look at all these molecules which have got emission lines in the waveband. And so it's a challenge to separate out all the chemicals. But what you want to do now is to actually compare that with biological chemical reaction chain. Don't memorize this. Okay. This is showing you all the sorts of things which you now need to make prebiotic molecules. And so there's a lot of work going on. In the Cavendish, for example, what we are doing, we're setting up a laboratory where we simulate planetary surfaces, put in all of this stuff, and then see what happens. So this is the sort of thing that you're doing in the lab to be able to support these observations. And even if you detect these things, you've still got the problem. How do you make sure it's something that's got an atmosphere like the Earth? And these are just examples. Here's any host stars, but it might be non-condensable gas. There might be no oceans. It might be an M12 with habitable CO2 rich. You know, these sorts of things. These are, again, more challenges to actually say, how do we distinguish what's going on if we find all these molecules? Well, that takes us directly to where the stars are actually formed and came about. And that's another great area that's developed no end. This is a beautiful picture, the optical picture of the Orion Nebula, which I suspect you all know, and that wonderful picture of that. But the trouble about it, it's full of dust. And the dust is obscuring all the most interesting areas that you want to study. Where are all the stars in the Orion Nebula? Well, the answer's easy. You go to 2.2 microns, and here's the image, again from the Hubble Space Telescope, of the same region, but now you see it's been cleaned up. You just got to clean it to come and clean up the picture. And now you see all the stars, and here are the young stars, and here are the protostars just in the process of formation in the Orion Nebula. Now, we've got a pretty good idea now how the stars actually form, and here they are here, just condensation out of a large cloud, and as it collapses, it's going to form what we call these accretion disks round about the newly formed star, and eventually that will become a solar system-like system with a star in the middle. So the general outlines is very good, but the details need to be understood. Now, this is where we need something like the ALMA observatory. And the ALMA blows my mind. Interferometry is difficult. But now you've got to tie together 66 telescopes in the most difficult waveband, the millimeter and sub-millimeter waveband. And it all works. It's a fantastic triumph of technology to make this work. And among the most, this is in Chile, I think, as you all know, 66 telescopes on the Atacama Desert at 5,000 meters. So it's a challenging place to be. It's lovely, beautiful. I love it. I've been there many times, and fortunately, I survived. You know, at that high. Whereas I was able to survive without additional oxygen. That proves I'm young. Okay, so there we are. Anyway, among the first pictures that were derived were this one, and this completely blew my mind when I said, "Look, this is it. This is what we wanted ALMA to do. Let's actually put the whole process of planetary formation on a proper observational basis." Now, this HL Tau here, it's a very young star. It's about only 450 light years. It's very, very close to us. And its luminosity and temperature tell us that its age is less than 100,000 years. So that is really a very small baby, right, in cosmological terms. And these are the sorts of systems that we can study to understand star and planet formation. You can say, where would the solar system fit in that map? And there it is. So you're already down at the sort of scales where you can actually hope to be able to detect systems like our own solar system in these planetary disks. This is fantastically exciting stuff. Now, what about the insides of the stars? Now, this is another subject which I find absolutely fascinating. And this is the way in which you can detect now the vibrational modes of the sun by what's called helioseismology. So up till recently, there was no way you could work out what's happening inside the sun. You had to deduce it all from very good physics. But now you can look at all of these oscillatory modes of the sun, and you can see it's a fantastic spectrum with lots of rotational splittings of the lines as well. So you can get a vast amount of data out of these sorts of studies. Well, here's just one example of what came from the Soho Observatory. What this shows here is the inside of the sun, and if it was the simplest of straightforward models, it would all be yellow. And so these colors are showing the deviations from the smooth model for the inside of the sun. And there's some wonderful things. Look at this extremely sharp dividing line between the convective zone in the outer region and the radiative zone inside. You know, that's the sort of information that you really need to test the models of the stars. And remember, we've got to get the stars right, or we're going to have real trouble doing this on very distant galaxies. So this is terrific stuff. You can also get the internal velocities of inside the sun. Again, this is something that, again, is absolutely a gift for the stellar modelers. Here you've got the poles that are rotating inside the sun more slowly than they are in the equatorial regions. So again, this has got to be modeled so that we can get the models of the stars correct. Now, you can then extend these ideas to what is called astroseismology. Now going to extend other stars and seeing how they vibrate and then working out their structures. And at this time, we've got these are all types of stars which have been detected as vibrating objects for which we can then work out the internal structure. So people who want to model for example, the stellar contents of galaxies, they've got to make sure they've got it right. They're going to be using this type of data to confirm the models of the galaxies. Now, of course, the end point of stellar evolution for massive stars is to make black holes. Everybody knows that. And so just very quickly, let me forget about the solar mass black holes and go to the biggies, the big ones. In particular, this is the black hole in the center of our own galaxy. Now, this is an amazing picture. Again, everything I'm showing you this evening is an amazing picture. And you know, I'm sorry to say that, but it's true. That's all I can say. Now, this has been a tremendous piece of technology, because this is not just by photographing what's going on in the galactic center. It's taking it with infrared adaptive optics. So you had to get, again, a large improvement in the positional accuracy of the stars before you could track their motions. But this is what is actually seen until very, very recently. These are all the elliptical orbits about the black hole in the galactic center. Now, let's look at a slightly earlier picture, because it shows rather more simply. Look at this one here, this one, S2. That star, in 15 years, made a complete circuit round about the black hole in the galactic center. And so from that, you can get very accurate measures of the mass and so on. So this is a tremendous example of how you can measure the masses of black holes in the centers of galaxies very, very accurately. So you've got to ask, how do you do this on all the other black holes? Right? It's a big, big challenge to go further, because our galactic center is quite close. Well, what you find is that the central black hole flickers. You see it flicker, it's not constant. And that's because matter is pouring into the black hole, and therefore it's emitting radiation. So we've got to look at accretion disks about black holes. We believe that, again, there are these black holes in the nuclei of almost all massive galaxies in their nuclei, from our nearby neighbors like M31 to the really big, massive black holes in M87, NG4151, and then the first quasar, 3C273. That's the quasar, and these are galaxies at the same distances as the quasar. They're hyperluminous objects. Now, let us do a little bit of black hole physics and the accretion disks about it. Because of the rotation, a rotating accretion disk is formed about the black hole as the matter falls in. That's because the matter falling in is bound to have some angular momentum or rotation, and that then causes things to flatten along the rotation axis. And that's what happens here. So this is the disk that's formed about it, but there's a big hole in the middle. And that's because, according to general relativity, there's a last stable orbit at 3 times the Schwarzschild radius here of the hole. So there's here a region where there are no stable orbits for matter which falls into the black hole, and that's very important. So that's what you want to try to study. Now, the way it works is that the energy for these objects is produced by the accretion of matter in the disk, but the disk has got friction or viscosity, which means that as the matter rotates, it begins to shrink in towards the center. So here is my PowerPoint simulation of what happens in an accretion disk looked at from above. So if we do that, there's my little blob of matter, and then what it does, the effect of viscosity and friction is it moves into a closer and closer orbit until it gets to the last stable orbit, and then it's gone. That's rather nice. I spent 1 day doing that. Okay, I shall do it again because I think it's rather fun. But it shows you what the physics of how you power the black holes is. That they would be circular orbits, except for the fact that the friction does 2 good things. It gets rid of the angular momentum and also produces a large amount of energy. So, as a great treat, I shall go back and put the blob there and run it again. And you should set this up as a problem to your student. Make a nice simulation like this. And there it goes. Now watch carefully, look at the redshifting until it goes to the final Schwarzschild radius and becomes black. Okay, the students have got to do all of that. Okay. So that's how you release the energy. And so that's very good. But how can you now find evidence this is actually happening? Now, this can be done in the X-ray waveband in a beautiful experiment of looking at the spectrum of an iron line, a fluorescent iron line, in the X-ray waveband. Now, if we were dealing with ordinary Newtonian gravity, then you would get just a single line like this in the X-ray spectrum. But now we've got to remember that we've got to put in gravitational and relativistic Doppler shifts. And that's going to affect the appearance of the line in ways I'm going to show you in the next series of slides. So if you do the computations, then what you find is that the spectrum should have a tail on it like this. All right? And that's because some of the radiation is coming from the innermost regions of the accretion disk. So, for example, some of it's coming here from the last stable orbit about the black hole. This most redshifted radiation is coming essentially from the last stable orbit about the black hole. So, there is evidence we are seeing radiation coming directly from the last stable orbit about the black hole. So here's an observation, and this is this active galactic nucleus, and here's the spectral line. There it is with a long tail on the end. When you say, that's it, right? You're actually seeing the radiation coming from the accretion disk. The only worrying thing is this is the only good example they've got. Right? So it's not always going to work, but you've just got to keep looking again with more and more sensitivity to see how well it goes. But that's rather compelling. But there's something else that we've done wrong. And that is we've actually shown the disks as disks. And we haven't yet taken into the effects of general relativity and rotation on the images. Now, if you do this, you find some really rather beautiful pictures. So here is a black hole with an accretion disk at an angle of 70 degrees to the vertical. Okay, so we're not looking at it face on, we're not looking at edge on, we're looking at an angle of 70 degrees. So the question is, what do you see? Now, this parameter here is the amount of rotation relative to the mass of the black hole. There's a maximum amount of rotation you can have of the black hole. So this is the maximally fast rotating black hole. This is one with no rotation, and it looks like that. Okay, so they're very distinct pictures. Now, where do these things come from? Well, that's rather fun. Here, computations by one of our past graduate students, Yuri Dubrovsky. And we're going to just look and see how these various bits of this picture come about. So, for example, here, this large arc here, that comes from radiation from the underside of the backside of the accretion disk coming out and towards the observer in that direction. Okay? The next one, 2. That is coming from the nearest side, top side, going around the black hole and going off in that direction. Okay. Number 3, that's going from the underside of the nearest side, going around the black hole and going off in that direction. And the last one, 4, that is from the far side, going around the black hole and going off in our direction. That's just showing the trajectories of light through the bent space-time in the vicinity of the black hole. Now, some of you who go to the cinema may recognize this picture. If you actually went to Interstellar, I don't know if any have you been to see Interstellar, then this is what they show. You see, they've got it right. And the reason they got it right was that it was Kip Thorne was the scientific advisor to the program, so he was going to get it right. So this is why we call it the application of astrophysics and cosmology to life. Right? You couldn't do it without it. Anyway, that's it, right? And there's the little spacecraft about to do dangerous things. Okay. In fact, it's interesting that Kip, when I talked to him about this, he said 3/4 of the film is great. I agreed with everything that they did for the first 3/4 of the film. For the last quarter, when they tried to demonstrate going through multidimensional space-time, I gave up. He didn't like it. Well, there's a wonderful bit in physics where you don't quite know what's going, where lots of boxes seem to be on top of one another, and that's trying to represent what happens when you're trying to go back in time and do things. Now, remember that so this is not in my script, but this is great fun. That one of the rules about general relativity is that you can go into the past. In particular geometries, very complex geometries, but you can't change the past. Right? So you can be there and observe, but of course people would have seen you there anyway as well doing it. But there's one bit at the beginning when you see what look like poltergeist shaking the house. And then later on at the end, you discover that that's actually this chap has come through space-time. You can't change things, but that's the same things he'd done. You get the idea. So that's great fun. So one of the great recent observations has to say, do we see anything like that about the nearby black hole? And this is a tremendous project, the Event Horizon Telescope, where all of these telescopes were working at the highest frequencies they could get to get the maximum angular resolution. And technically, this is a fantastic challenge again, but they did it, and looking at M87, they got that picture. All right? And that is exactly what we are seeing in the Interstellar picture. Interstellar is there for us. It's just pretty black, you see. Not bad, is it? Anyway, that's terribly exciting. The fact that you could actually now model these. Now, this was pulling out every possible stop to make this experiment work. But again, once you've got it now, then you can go and try to see where we go in the future. Now, of course, now that we're talking about black holes, we've got to talk about inspiraling black holes producing gravitational radiation. And this is one of the really great discoveries of the 20th century. I never expected to live to see this, I've got to be honest. I thought it was too difficult, but it actually has been made to work. So these are the predictions. If you've got an inspiring pair of black holes, there they are there, then as they spiral in, they lose energy by gravitational radiation and go into smaller and smaller orbits and eventually merge and produce a single black hole. This is pretty extreme stuff. Here are the velocities. You see when you're going into the black hole, these black holes are going about each other at half the speed of light. That's quite some thought. But we've seen it happen, and it's absolutely, utterly convincing that that's what's going on. So let me just show you how it works. I'm sure you will enjoy. I love showing this one. This is now modeling the first detected source. So there are 30 solar mass black holes. So we just set this simulation going. And the times are the actual times that will appear in the picture later. So these are the two black holes, and they're the seconds relative to the point where you're at maximum stress for the two black holes. You've slowed down this. Here they are, the two black holes. Now that's it, just about to go. Off it goes into one black hole, tilt away, and there are the gravitational waves going away from the system. That's a great simulation. Shall I do it again? Yes, good answer. Right, so that's what's going on. You can see they're going about each other, and they're coming in closer and closer orbits as they go in. The lines are showing the way in which the matter is flowing. Now you're within 0.1 of a second of the point where they just begin to touch and begin to coalesce to make one black hole. Just pause a moment, and then off it goes, making a single hole, and there's the huge amount of gravitational waves being set off. So it's what we're trying to detect. But what we're trying to detect is a very tiny strain on the detectors. Well, I'm sure you've all seen this. Here again are the two detectors of the LIGO array in the USA, 4 kilometer arms, and fantastic sensitivity. Now, there's another bit of technology which I will tell you about, which is the program began to be fully funded in 2002, and the first detections were made in 2016. All right? Funding agencies don't like that. Right? But they said at the beginning, we are going to get from a level up about here, way up here, way up there, and we'll be incrementally improving it over that time. And they did it. And that's inspired funding for the in the American system. Well, there was the answer. And whenever any of us saw this, we said, oh, that's it. There's no question about it. That's the signature of gravitational radiation. There are the observations from one of the detectors, this from the other, and this is what they look like when you do the best fitting curves. Absolutely spot on. And so here was the result of that. 30 times the mass of the sun, the two black holes, they move about each other about half the speed of light. 3 solar masses of matter are converted into the energy of gravitational waves in less than 1/10 of a second. That is what I call really high energy astrophysics, right? Converting 3 solar masses of mass into gravitational waves in 0.1 of a second. So that's tremendous stuff. Now, by 2018, this is what the diagram looked like for the masses of the final ones relative to those which are coalescing. And you see there's 1, 2, 3, 4, 5. These are black holes detected from X-ray binaries. And here's the first of the neutron stars coalescing to make what we don't quite know what it actually made. If I look at what happened this year, there's the same diagram this year. And again, they upgraded the system yet again. And so here, there's huge numbers of the black holes here, and including 1 or 2 coalescing neutron stars as well. So That's what you can do with what is now three detector systems, including the Virgo one in Italy. If you put more in, you get better and better positions, you get more sensitivity. This is the beginning of a big story. Now, we're doing pretty well. Let's now have a little look at cosmology, because that's, again, the province of general relativity as well, which we've been testing with that. Now, I start with this nice picture of a Hammer-Eitoff projection, which is the way of being able to project a sphere onto a flat sheet of paper. So you'll see that things get distorted, but at least you can see the whole surface of the sky in one picture. So if we look at our own Milky Way in this system, here is the Milky Way, the center of the galaxy, and so forth. And then the coordinate system is distorted up here, but at least it looks good. So that's just to orient you for the diagrams you see in a moment. The first map comes from the Kobe map back around about 1994, 1996, and it's one of the most spectacular images in astronomy. I'll show you it. It is utterly unbelievable. There it is. That's the whole sky seen by the Kobe satellite. It's incredibly uniform over the whole sky. For the cosmologist, this is a dream. Because what it means is that you can start doing your cosmology with isotopic homogeneous world models, which are nice and easy, compared with the full thing you would have to go. If this would end up looking like a mess, we would be in trouble. There's no question about it. But this simplifies everything so enormously that we can do very, very clever things. If you go 1,000 times more sensitive, you get this map. And you're beginning to recover now the plane of the galaxy here. But here is the motion of the Earth through the frame of reference in which it would be completely isotropic. And so you can actually measure your velocity relative to an absolute frame of reference. Ask questions about relativity later if you're worried about that statement. It's all perfectly fine. And then if you go another 100 times deeper, this is what you get. And so here you are now, you've recovered the plane of the galaxy. There it is there. And you want to get rid of that because that's messing up the picture. The ripples in the background at the high latitudes are indeed genuinely ripples in the background radiation. And that was the first bit of evidence we had for what it is that makes the galaxies. So that has been a huge subject, and at the conference I'm sure you've got this coming out of your ears. You know, it's just so fantastic. It's so much fascinating physics that goes into analyzing it. Now, that radiation then comes from what we call the last scattering surface, when the universe was sufficiently hot to be able to ionize the material, the hydrogen that was coming from the early universe. So in round figures, here's us about probably 13 and 700,000 years from the beginning, and here is again at 370,000 years from the beginning. But that is a barrier, because at that point all of the hydrogen becomes ionized, and so the radiation gets scattered and you can't see any more structure. So you see here the ripples I've shown there are meant to represent ripples on that last scattering surface, which is what you saw on the map of the microwave background. Now, the Planck satellite, the European satellite, did an absolutely fabulous job in now looking in high detail at what's going on. And there's a set of about 100 papers altogether, just analyzing in detail very beautifully what's going on. So let me show you what you had to do. If you look at the total map of the sky, it looks like this. So you don't see much of the stuff that you're trying to get at, which is the fluctuations in the background. But fortunately, he's produced this nice video showing you what you've got to do. So this is revealing the cosmic microwave background. So we start with the overall picture of everything, which is this one here, and we've got to take off all the individual sources that are present. So you map all the sources, and then you take them away. Like that. I'm sure you've seen this video before, but it's a great one. Now you take away the radio emission from the Milky Way. You model that as the synchrotron radiation. Take that away, and you're left with that. But you've still got the dust emission from the Milky Way, and so you've got to model that, and then take it off. And when you do that, that's what you get. So you've got to have absolutely fantastic control of all the systematics before you get to that map, and that's a great, great challenge. Now, I'll show you one of the other favorite diagrams I've got of this final version. And that's this picture here. Now, it turned out that I was the chairman of the committee that had to make a decision. Do we put a high-frequency instrument or a low-frequency instrument? And I insisted we fly both instruments, right? Because you need to be able to get the same sky observed with the same telescope system, although we've got different instruments. And so, let me put it politely, there was a degree of competition between the French and the Italian groups. You know, it was almost friendly competition, but they were. But the important thing about this was the instruments were entirely independent. They both wrote all their own software for analyzing and doing all the things I've just said. Then produced the maps of the sky, and then they took the difference between the map here at 100 gigahertz from the high frequency instrument and the 70 gigahertz from the low frequency instrument, and that's what they got. Now, what you've got to do, this is spectacular. I kid thee not. Look at the smooth. This is random Gaussian noise that we're seeing all over the map here at the levels that they claimed the accuracy. And what that tells you, that's as close as you can get to independent evidence on how good the two experiments are. So, the results are great, but this is fantastic. They did it. So that shows you just what the quality of the scientists and their procedure. It was a huge effort, but it was tremendous. But of course, now we've got to say, well, that's great, thank you very much, but how do we make the structures in the universe, given that we've got all of that stuff looking so uniform and beautiful? This is the large-scale distribution of galaxies going out in redshift here in billions of light years. And the distribution of galaxies looks like a sponge. That's the best thing to describe it. Now remember, a sponge is a great thing because the material of the sponge is all held together. But the holes of the sponge are also all held together. In other words, it's a very special topology in which you've got the matter and the holes all together. So you've got to make these structures in the models that we devise. So there it is. That's the problem. Get this from one to the other. Now, I'm going to show you the results of some of the simulations, and they have come out very nicely. Don't bother about the details. We've got dark matter and dark energy, which people always ask about, and so forth. We've got to put in a spectrum of the initial ripples, because they can't be random ripples. They've got to have a spectrum. And we knew beforehand it had to have something like this. There's a power spectrum. Don't worry about power spectrum. Just take it. I'm a cosmologist. Trust me. That was a joke. And then you put in ordinary baryonic matter, ordinary stuff that we're made of, which amounts to just about 5% of the total mass. Well, I'll show you the results from the formation of the Millennium simulations, which are really terrific. And what happens, we start off when the universe is about 1/100th of its present age, at a redshift of about 20, and then we watch the development in what we call co-moving coordinates. So to see what's going on, the universe is expanding, but we take out the expansion so you can follow the evolution of the individual bits and pieces in the picture. So here it is, and we're starting at again when the universe was only about 1/100th of its present age, and then we let it go. And so it's coming down in equal time steps. It's a nonlinear function of the redshift, but just watch what happens. This just evolving under gravity, nothing else. And now you begin to see all the structures that we see today beginning to appear. You see, we're beginning to make clusters of galaxies, big holes, stringy structures, and everything. And this is really essentially the minimal number of assumptions that's being made to actually go into the simulation. This one's done by Volker Springel, Max Planck Institute Professor. So you see what we've got. We've got this stringy structure. We've got clusters of galaxies. We've got all of that stuff. We'll see this again later. But it's pretty compelling that we're basically along the right lines for understanding how the large-scale structure came about, despite the tremendous smoothness of that. Now, we've got to quantify that. And I'm not going to go into the details of this. That's great fun. But all the people who were at the school know this backwards, and you can do all the Fourier transfers, blah, blah, blah. You know, I'm not, forget it. I'm going to. The important thing is that there are very clear predictions that, again, the fluctuation should be smooth like this on very small scale, on large scales. But then there are these wiggles which are predicted to happen on scales of 1 degree and less. So these are what we call the acoustic peaks, and they're called that because they genuinely are sound waves on the very, very large scale. But why do you get these great big peaks like that? Well, there's a very easy way of understanding it. Here's what happens for the first few of these perturbations here. You see, there's a horizon scale when the size of the perturbation is the same size as CT, the age of the universe times t. That's just the biggest scales that you can get. So that's there. And then this is one about half the size, a third the size, quarter the size. When they come through the horizon, they suddenly become sound waves. Right? And so what that means, this one will just collapse on this. This is where the radiation is being coming to us. This one has got half a cycle, and that'll got denser. This one's got through the cycle, 3/4 through the cycle. This one's got again back to where you started. Right? So what it's saying is that because of this phenomena here, you get these sorts of structures where you get great big peaks when you've done half a cycle or 3/4 of a cycle, because the universe can't distinguish positives and negatives. And that's where these shapes come from. They also lead to what are called baryon-acoustic oscillations, which is just the same sort of phenomena, but now in the distributions of galaxies. Well, there's the result of the Planck spectrum, the Planck experiment. And it is utterly and completely mind-blowing. Right? There's a vast number of data points going into this. You can see there's the fit to it. And yet you can define all of that by a 6-parameter family. Right? And that is pretty good going. You know, we can't be too far out to get that answer right. So that's fantastically encouraging. And we get out of that, here the baryon-acoustic oscillations, which again occur at almost exactly the right spot again for the model that we are talking about. But you can do more. You can actually get the properties of the dark matter directly from the CMB. And that's because the radiation has got to go through all these ripples of large-scale structures to get to us here. And so if you are very clever, which fortunately all the people at the school were, you are able to actually dig out the effects of that upon the distribution of matter in the universe. It's a tremendous stuff. So what you get in is this map. And this is showing you now the distribution of dark matter projected all the way back to the early stages, except most of this happens at rather low redshifts, in fact. But it's also correlated with a large distribution of matter. And so, no, don't memorize this. This is just showing then the results that you get from the experiment. You can define everything by these 6-parameter model here, and then the rest of them are all the derived parameters. But the utterly mind-blowing thing about this is that you can do the whole of cosmology on the basis of Planck alone. You don't have to know anything about the optical universe. You don't have to know anything else about the universe other than the microwave background, and you get all the parameters. I hope that surprises you as much as it surprises me. But it's a tremendous result. And then what it means is, when you look at all the other cosmological tests, they are providing supportive evidence and can be refined on the basis of what we've got from the CMB. This doesn't make me popular with optical astronomers, I may say, when I say this, but it's true. Anyway, it's great fun. Well, that's a terrific achievement. And we end up with this rather annoying picture of the distribution of mass in the universe. So this tells us that the ordinary matter that we are made of is 5% of the total mass. The dark matter is about 26%, and then this dark energy is 69%. And that's jolly annoying, because we don't know what the dark energy and the dark matter are. But that's good news for all young people. You've got something to chase. Right? You've got to solve the problem of what the nature of dark matter and dark. I won't solve it, but you will. I'm absolutely confident that you will. So what you get out of all of this is, first, amazingly, and this is a very strange thing, if you add everything together, we live in a geometrically flat universe to fantastic precision. The value should be 0 if it's completely flat, and there's the answer, 0.007 plus 0.0019. Now, there's something, I think, very fundamental about that we haven't quite got to the bottom of, because there's a priori no reason why that should happen, even less reason why the sum of the dark matter, dark energy, and the baryonic matter should come exactly to be a flat universe. That should worry you. It worries me, but it's a really big, big challenge. Then we've got the ionization redshift, which comes out rather precisely 7.8 plus or minus 0.71, and you will see the implications of that just in a moment. So my summary is that the dark matter is a difficult problem. The good thing about it, it gravitates, right? So it means we've got at least some hope of being able to find some sorts of gravitating particles or materials that we'll be able to do. Haven't found it yet. We just got to try harder. And that's, again, look at these very difficult experiments to see if you could nail it down. But the dark energy is very difficult. And if you look at the equations, the reason I say that is that the lambda term of the dark energy only appears on the larger scales. That's where it has its... You can't do a really local experiment to be able to find it very satisfactorily. So that's very hard. But there are other things about this. If you really believe it's some sort of particle, we're able to do experiments in the laboratory now where you can create substances with the same equation of state as the dark matter, dark energy. And I think we may learn quite a lot from that. That's a really big, big challenge. Now, I'm getting towards the end. I hope you don't mind if I have another 5 minutes or so. Where the shift of emphasis now is not towards studying galaxies at the present day, but to look very, very far back, as far back as we could. Now, just until a few months ago, this was the picture that we had of how far we can study. What's happening here is the universe is cooling down, and it would get very, very cold, but suddenly it's got to be completely reionized. You've got to heat up all the ordinary hydrogen and helium in the universe to ionize it. And we know it must happen round about this era, that reionization era. And again, the Planck results did pin it down to somewhere round about here is when the median reionization will be taken. Now, even by that time, the Hubble has seen galaxies here or here, and that's, again, getting through to the cold side of the reionization epoch. Just, again, within the last month or so, we've got this picture from the JWST. And here, this one here has got a galaxy with redshift 10.5, and this one here is a galaxy with redshift 12.5. And there are reports of one with a redshift of 17. So what it means is we're detecting now objects which are right in this region here. There's redshift 12, there's redshift 20, and you can see you're almost looking at objects before all the action got going to reionize the whole of the universe. And we've got another 10 years of JWST. So it's going to be fantastic. We should be able to nail that problem. Well, again, there's what the very distant universe looks at, and the Hubble Space Telescope told us very convincingly that the structures of galaxies are very different at large distances from the ones that we see today. There's been strong evolution. These things are much smaller and much less massive than the ones that we see at the present day. So we need to understand that. And of course, the JWST will be wonderful for doing that. But first of all, let me just show you another simulation to show how we've got to tie together now the underlying dark matter which creates the structures and what happens to the matter. This is another of these lovely simulations which I love showing. So here's the dark matter. And here is the gas density on the right. And so all the driving is in the dark matter. And you see it's beginning to come together to make these stringy structures, these things, and then they begin to collapse towards a dynamical center, and the gas follows it, as you can see there. So here we're down to redshift 4, we're getting quite not so far from the present day, but you see things are beginning to come in, and the gas is falling into these potential worlds in the distributive dark matter. So there it goes. Now all the action really starts to get going here, because this is what's happening in the gas. You can see we've got a massive galaxy forming here. Here's the gas accumulating on that galaxy, and now you'll see things beginning to move rather fast through the structures. Down to redshift 1 now, so this is getting quite close to the present day. You can see there's the gas starting to coalesce to make the great X-ray halos in the clusters of galaxies. Great simulation. And at last, we've ended up now with the structure of a cluster of galaxies here, redshift 3, redshift 2, redshift 1, and there we are. So that's how we put it together. Now, again, here's another of the first images from the JWST, and this is showing what the universe looks like to it. And again, it's mind-blowing. You can see there's huge numbers of galaxies in this field. This is a 12.5-hour observation of a cluster of galaxies, and you can see these fabulous arcs all around about the center of the cluster of galaxies. These are gravitationally lensed images of very distant background galaxies. And so the young people in the audience have got to analyze this and get science out of it. That's the big challenge. It's a terrific challenge. If I were a young astronomer, which I by definition am, right, this is what I would be doing, trying to actually get inside what's going on. So it is. So the other thing which we are able to do with all of the new data, we know pretty well what the star formation history of the universe is, and that's got to be tied in with all the other bits of astronomy that we've been describing. And this is telling us that most of the stars and galaxies occurred, in the relatively recent past, redshift of 2, not in the infinitely distant past. And we've got to understand galaxy evolution. There are new ways of looking at the properties of galaxies. Rather than calling them spirals and all of that nomenclature, you can do it in terms of red and blue sequences. So there are some big puzzles. Why the most massive galaxies stop forming stars at redshift 2, how you quench star formation in elliptical galaxies, the downside, and so forth. Lots of things which are technical I won't bore you about. But here's just an example of what the problem is. The theory is giving the red line, but that produces too few massive galaxies and also too few small galaxies. So again, there's astrophysics that's got to come in to help to understand what's going on in these types of spectra. Well, we're almost there. Here is the equivalent of the first slide I showed you. What is the universe? What's going to look like tomorrow? And these are the legacy that everybody in this audience will have to work with, right? So we've got here the square kilometer array, or the largest radio telescope ever built. This one is well on its way now, and that will give us a factor of about 100 improved in sensitivity in radio band. We've got the EELT 38-meter optical telescope, which is now being built in South America, which again is going to take us deep into the universe to understand what's going on. We've got the Athena X-ray satellite, which will give us all of these clues about the hot gas, black holes, and things like that. We've got the LISA gravitational wave experiment, which will now go into space and detect other types of black holes and other phenomena in about another 8 years' time. And then perhaps in the future we'll get ATLAS, right, which is a 16-meter space optical infrared telescope, which will be a super-duper JWST. So that's more or less. I think you will gather that I regard the future as being extremely exciting. They're very exciting times that we're living in. Who would have thought you would have access to these incredible facilities? You know, I certainly wouldn't have thought it would have happened, but it is happening. The future is very bright and expensive. Thank you very much.
Thank you very much for the very enlightening talk. I will take the time to thank, because I think that there are a couple of generations of cosmologists and astrophysicists that have learned from your books and from your papers. And personally, I have enjoyed a lot reading your books. So I have learned a lot from you.
Well, you heard that? Go and buy them. Yeah.
And the question is, large-scale structure experiments now are trying to tell us that the main goal is to discover or reveal the nature of dark energy. So you have DESI, Euclid, all these experiments are more or less meant to this is the main target, like dark energy. Now, one might think that we will try to parameterize to a very high accuracy our ignorance on the components of the universe instead of revealing the nature of dark energy. So there is a small gap between these two things, I think, between saying the amount of dark energy is this number to this very high accuracy, or the nature of dark energy is this particular thing. Can you comment on that,
yes,
please?
This is, I prefer to use the word puzzling, right, rather than a catastrophe. You understand? I think this is very, very strange, and I think there's something quite deep going on that isn't quite being appreciated. The way I like to put it is that, you know, even at the level of looking at Einstein's field equations, are we sure it's a field that should be on the left-hand side, or is it something wrong with the geometry? Right? Now, I'm not up to date with the literature, but that is a sort of issue. You know, it might be that the lambda term is just the lambda term, and what would that do? No? But the fact that the sum of all of these is equal to 0, telling we live in a flat universe, is to me very, very strange. I can't think of a reason why it should happen right off the top of my head. But you know, I think there are many rather deep questions to be decided about that. I can't really give you a good answer.
Well, you say the future is bright, which it is, but the sky is getting too bright.
Yes.
What do you think astronomers should do to defend ourselves so that some of these wonderful, huge telescopes, particularly on the ground, can actually get the results we need?
It's very, very worrying, because these are absolutely scrupulous entrepreneurs polluting humanity's sky. That's what it is. We've had to deal with these sorts of things before. You know, when the level of the Schmidt telescope and all the satellites going across, producing streaks across them, which made lots of them. But this stuff is very insidious, because the sensitivities of our detectors are so incredible. Just one or two of these horrific things will actually blow the instruments out of the sky. Well, you know, I believe we need, you know, international legislation, which we've got already, to protect the skies. But you're not going to stop people making money out of putting nasty things up in space, unless we all push together to get the political will at governmental level that keep our skies pure.
Hi. I think you mentioned at some point that some scientists were studying, how did you put it? Something in the lab that had the same equation of state
Yes, that's right.
as
Yes.
dark energy.
Yes.
Could you give more details on that?
Yes. I'm not an expert in this area, but my guts tell me this is great stuff. It's particularly when you look at what you can do with Bose-Einstein condensates, where you've actually got the particles all it's coherent matter, and there you can actually adjust things so that you get negative pressure equations of state. Now that's been done in one or two cases. It's a big challenge to do it, but we've got a couple of experiments in the laboratory where we are aiming to do exactly that. This is where you've got, as you know, the Broglie wavelength is containing huge numbers of the particles, and so you're dealing with Bose-Einstein condensates en masse, and that's a good mimic for the sort of material with negative pressure equation of state. So I don't know what's going to come out of that, but we've got no other examples except the Higgs boson, and that's not exactly a gas. So you're not going to be able to use things like that to do it.
More questions?
Thank you very much. It was a very, very interesting talk. Really appreciate that. Like you, I was quite impressed to see the discovery of gravitational waves in my lifetime. I didn't expect that. The other thing that I wasn't expecting to see was the picture of the black hole, the Event Horizon Telescope. Was that just a one-off project? Is the Event Horizon Telescope still undertaking that work?
There's a sense in which it was a one-off project because this is the brightest example one could try to do it on. I believe that some people maybe know better than I do. I think there's a second one being done, which I seem to remember a report coming up. So it's entirely a question. Phase stability over these gigantic distances at the very short wavelengths is fantastically challenging, and so the fact that they were able to make it is a tremendous triumph. One will have learned how to do it from that, and so we can start going down in the luminosity to do other examples. I'm sure that will happen, but you've got to get an awful lot of telescopes collaborating together to make it work. I think it's a stunning thing they've done.
So we should expect some more.
I'm sure we will get more images like that. Yes.
Thank you.
So, questions?
Thanks so much for the nice lecture. I wanted to ask you, what is, in your opinion, the major breakthrough we are going to witness in the next few years in astrophysics or cosmology?
Well, it goes at all sorts of different levels. At the simplest level, I think the epoch of reionization is going to be much, much better understood, and what we've got to do to make that, how that feeds back upon the first stars and all that sort of thing. From the point of view of cosmological astrophysics, I think that's going to be a very exciting era. I actually hope we will solve the dark matter problem within 20 years. Right? I'm a great optimist, right? And I believe that it may well be some extremely massive particle that we don't know about that's going to do. We just can't detect them. I like the fact that this stuff gravitates, not like the dark energy, which is a pain, because it doesn't gravitate. It doesn't gravitate. Is that still astronomy? Right. And that would be one example. The gravitational wave experiments will be terrific, and when we go up into space, then we will see, again, a different range of black hole masses, much smaller than the ones that we're seeing in the. Everything I've talked about, I hope it happens.
Thanks.
Oh, let me just make one point. I'm very excited about the exoplanets and the search for their atmospheres and whether they might be. It's such a rich field. There's so many clever things that you can do. Original things by going between fields to get some good ideas.
Okay, more questions? In the meantime, do you think we will have a definite or closer answer to, to the question of whether there is life out there from this program of exoplanets, or how close we will get to know about this?
I think that's very hard. I think the best that one can do is, in my very limited ambition now, is to say, look, can we identify planets which have got the right characteristics, right atmospheres that it would be possible, and that would be terrific. But that depends on us being able to understand this very complex chemistry, and there are interesting challenges there. The ones I showed on that color diagram. And which we're actually doing these in the lab in Cambridge. What we're trying to do is we've got a special apparatus where we've got simulating rocky planet surfaces, and then we put in the things that we know are there, and then you change the physical conditions in the lab and see if you've got anything that looks like the sorts of biological species we need. I think lots of labs ought to try that and see where we get from that. Yeah.
When we talk about motion in the universe, we distinguish between motion with space and motion through space. With space, I refer to like goes along with the expansion of the universe. And my question would be, if an object is just moving with space and not through space, is that object at rest with respect to the CMB? That is to say, there would be no Doppler shift anywhere in the CMB.
Yeah. If you look at the fundamentals of all the isotropic homogeneous world models, the key point is the cosmological principle, which is that every point in the universe is equivalent to every other point on that approximation. What that means is that us here looking at Hubble's constant of the expanding universe, exactly the same thing will happen at the same epoch at what is in our quasar redshift. So I think this is one of the things that I'm sure everyone's learned. You've got to be very careful about understanding how the cosmological models are set up. They are required to be the same at a given epoch on average everywhere. So you do get things moving through relative to the local standard of rest, but it's best always to think of one bit doing the same thing on its own in different bits in the universe, or else you get into trouble.
Okay. Do you want to close in?
Try to be quick. I think we're lucky that there are many things we don't understand yet, and we're developing the tools to actually address all those things we don't understand in the universe. Do you foresee, as a possibility, the situation in which we understand almost everything? Say, in the next 50 years, we get lucky and we detect gravitational waves from the cosmological background. We detect dark matter, we identify dark matter. We even understand dark energy, or we find the field that generates dark energy. Then we sample ionization. We find life in an exoplanet nearby. Do you conceive as a possibility that in 100 years our grandchildren will be bored to death because they have nothing interesting to find?
No.
Why not? Why not?
Absolutely not. Because, as you know, whenever you push these experiments a factor of 10 beyond where you are now, something totally unexpected turns up. And in a sense, I hope that's where some of the solutions of these big problems come from. I'm not being what's the word? Advocate for the technology, but I think people need to look hard at what you need to get these factors of 10. It's whenever you get the factors of 10, that's when new things appear. However well you think you understand the universe at the moment.
Thank you. Is there any other question? I feel we're still continuing the winter school. If there are no more questions, we say a big thank you to Malcolm, who has intensively given many seminars over the last 2 months.
Thank you.